Hello. You guys are right on time. I really appreciate that. Let me just make a second. Oh, hi. Who's that? Is that Aim?
Yep.
Amber.
As usual.
Amber?
Say again?
Amber is your name, right?
So unfortunately my email is still stuck with that, but I've actually changed my name.
Because I noticed, did you go to the talk yesterday? Because somebody named Amber was attending that talk. The unreasonable effectiveness of it had to do with homonyms in different languages. Was that you or somebody else?
I was. I don't think I was at that one. I went to the first thing that was in the morning, but then I had work the rest of the day.
Yeah, it was an interesting talk. I guess you would call that. The talk was on pseudo-linguistics or something, but they're trying to compare different languages, and it never occurred to me that to analyze homonyms, we have a lot in English, but I didn't know this, but in Korean, there's not that many. And I heard that in Chinese, there are some, but Chinese is not really, it's not what they call a written, doesn't have an alphabet. So they didn't consider that, but they compared English, French, Turkish, and in Japanese to some extent. It has an alphabet, and in Korean. And well, they had some theories, whatever. It was for fun. The talk was really for fun. But I saw somebody named Amber was part of in the audience. Well, maybe that's AIM. I don't know. Maybe it was. Yeah. So the speaker talked about a lot of things, and one of them was the unreasonable effectiveness of mathematics, and as of course they're talking about how it works so well for physics and the physical laws being so nice and so efficiently expressed in mathematical notation and stuff like that, and I can tell you the whole time I'm sort of kind of feeling like, no, you guys, you don't understand. I mean, you do algorithms to realize that it's not good. It's like trying to classify. If you're trying to look for the best algorithm to do something, it's kind of like classifying snowflakes. There's so many different things, and after a while, you realize there's more snowflake patterns, construct designs than there are like atoms in the universe. The speaker was just not familiar with the algorithm field, I think. Wow. Well, this has been a long week, and it's not over for me yet. I will not be able to make my office hours because I will be talking to my chair about this project I've been working on, committee work. So just awful. Because in order to be ready to talk to him, I'll have to skip my lunch today. So I'm sure you guys have been in this situation in your lives. And, if you're a glutton like me, skipping lunch means a lot more than most people. From Brandon. DoorDash and food. I'm in my office. I don't know if they can park and dash in.
Well, you'd be surprised. You can't get stuff delivered on campus.
Really? Because they're not legally supposed to be here. This is a closed facility.
Oh, well, then in that case, I don't know. But you can do deliveries to college.
I mean, there's been times I was so desperate. I look for a vending machine, and then I say to myself, you know what? Vending machine is operational, but it hasn't. Nobody's changed the food in there for like 2 years. It's like, oh, well, it's amazing, soft drinks, it's actually a stat problem. It turns out if you store soft drinks that use artificial sweetener, if you store them at room temperature or higher than room temperature, that sweetener breaks down and they become sour. And so somebody's bought, they went to Costco and they got a ton of diet Pepsi or something, or whatever. And then, I got all this as such a, and then they realized after 5 years, this stuff it's not only flat, but what happened to the sweetener? They do a statistical test and they have to see the effect, and they have to then measure the sweetness. And so how the heck do they do that? Because we know that we're all different, right? Some people detect sweetness a certain way and some as others. So you actually have professional tasters that can differentiate. They have a 10-step scale. And they actually can, these guys actually, and so, you have a lot of them. So you have to use statistics, what do you call it? You have to do you have to do inference for the mean, which we'll explain later if we have the time in this class. All right, so what did I promise you? Well, it's supposed to start the next chapter, but let me just give you a taste of what's coming, and then we'll go back and do the boring stuff. So we talked about some interesting problem. It's quite old, but it's called the Buffon needle problem. I just want to give you an overview of that. So Buffon needle problem, very famous. It's famous to the chagrin of mathematicians because a biologist solved this problem, not a mathematician, which is really rare. I mean, it wasn't that old. It's not like from the Greek times. It probably was 1840 or something. But what is the problem exactly? Let's see if I can do this. It's a little bit tricky, you guys. Geometric probability can be really tricky. So the situation is this. We've got these grid lines and irregular grid lines on a floor. I mean, this is sort of a avant-garde kind of floor, and they're all supposed to be at the same distance apart, d. And now you have this needle, and its length is, let's assume it's less than or equal to d over 2. Uh-oh. This, I got to be careful. Let me check my notes real quick. No, let's make it less than or equal to d. So the length of this needle is less than or equal to d. And now it gets complicated. You are going to grab this needle and throw it down on the floor here. So you see the grid lines, right? You can see my feeble attempt to make these uniform. Okay, it's supposed to be parallel. So what do you think the probability is that we have to evaluate here? So, okay, before you say it, I think some of you know, before you say it, let me tell you something about the answer. In fact, let me give you the answer. The answer is, I'll put it over here, 2L over pi times d. Now, there's a couple of things to say about this. That's the answer for, I haven't given you the question. So you have to reverse engineer this. you have to reverse engineer this. So that's the probability of what do you think? Well, let's see. If L and D were about the same, so there's a needle here, about that's D distance, then 2 over pi, what's 2 over pi approximate? A little less than 2 over pi is like 2/3. So what would have a 2/3 probability of happening if you throw this needle down? What do you think? A needle the same length as this, you just throw it down. Well, one thing, there's sort of two outcomes here, okay? If you look at this correctly, there's two outcomes. What are these outcomes? I throw that needle down and what? What or what? Somebody's got a chat. I bet you they have it here. Parking lot. No. Well, okay, if you want to see it's a parking lot, except you wouldn't just be flopping down, you know what I mean? You'd be driving in. But I guess some people park so terribly, and myself included, that it's almost like they just was a needle thrown down.
That was from a lot earlier.
But it's appropriate, right, for the parking?
Yeah, sure.
Park.
Well, what I'm gonna guess is it's the probability of hitting a line or hitting.
Is that a guess? I thought you knew this from 341. You know, very good.
Problem.
Very good. So you see about a 2/3, 60%, 65% probability if you throw that.
Reasonable.
Yeah, it's reasonable. But the thing is, how in the world do we? How do we? Again, this is kind of like that talk, the unreasonable effectiveness of mathematics. Mathematically, when you think about this, what do we need to do? You just don't. You know, it's one thing for the needle to land somewhere, but it's more than just landing. So imagine the needle had landed here, say. Okay, there's the center. It landed there. Maybe a little more needle. It's always good. It's one thing that it can land anywhere it wants, right? But there's another aspect to this. And so I want to be able to characterize all the ways that matter to us, because we're talking about hitting a line, or not hitting a line. All the ways it could land, just the equally likely things. But is it enough to say, well, okay, the center's here and center here? I mean, how to break this down so that we can analyze it? You see, it's once you see the math, or we spend some time with it, say, oh, that's natural. But when you look at it like this, how would you? What do you mean by, I mean, here's one that didn't hit, right? And maybe here's one that did hit. Okay. So what's a way of generating or taking into account all the equal likely, I would say, not just positions, but orientations, right? Because what matters is the orientation relative to one of the lines, right? So it would matter, whether it does or not, right? So this is, to me, this is what I don't like. I didn't like Ross's explanation, because I think the hardest part is to see this as a two-variable problem. There's two random variables. I mean, it's uniform, right? Because, I mean, the center could be, it doesn't matter, right? This is repeats, right? So the center could be anywhere. So the center, okay, boom, now you got the center. The center of the needle's right here. But that's not the whole story, right? It's not the whole story. Let me help you say this. So we randomly choose where the center of the needle, right? It's uniform. It could be anywhere here. So take a look at this fact. Here's the center, right? The center line. And now the needle, you see, if the center of the needle, if it's over here, then we should only be concerned ourselves with the cases where it's closer, which is the nearest line, okay? Which is the nearest, that's what we should, so really we only need to consider distances of the center to here. You might say, well, what if it's down here? Well, okay, that's an equivalent thing, if we're talking about, uniform distribution of the center. You know what I'm saying? So if this is the center line here, we can assume without loss of generality that the center of the needle is here, between here and here.
Before we keep going, just to clarify, what's the area that we're looking at? Like, is it, do the lines go on forever?
Yes.
In both directions?
Yes.
Okay.
Yes.
And then above the line, there's nothing?
No, lines keep going further. This is an infinite.
Okay. It's okay.
So, but there's this, this is very much how physicists apparently think, They say, well, all that really matters is the closest line. I mean, we really think, we consider the center could be anywhere, right? Anywhere on this infinite plateau here. But the thing is, all that matters is really, for our model, we can just say, okay, the center of the needle is in this region, okay? Yes, whatever it is, you see, it would be, we could just then start analyzing the problem from that. So if it's here, we'll just say, okay, this is what we're at. This is our situation. It repeats, in other words. Whatever we're going to do repeats. So we only need to consider to the nearest line. Okay, so, but still, nobody's said it yet. Does it help then to say what the distribution is of the center from the nearest line? So that would be what? So the vertical, so that distance would be uniform with what? From 0 to the nearest line to the farthest away would be d over 2. So now you can sort of see, how. But there's this missing element now. This is what makes this a classic problem. So yes, you throw down the thing, but this is a needle. It's got length. It's not just a point, right? If it was just a point, then that's an easier problem. But this needle has what? Well, the thing is, you have to understand there's two independent things that can change here. Where the center goes, and then what? What?
Like the rotation of the needle.
Yes, and those are independent. It's like they're separate. That we can agree on, right? We can think about that. You throw it down, it might spin a little bit or something, but it's those are independent. Where it landed and its orientation are different. And the same thing. Now we're going to blow this up a little bit. I'm not going to erase the answer because there's something about the answer that's pretty interesting. What is it? Pi. So somebody circle something. The problem is stated originally didn't seem to involve any circles. So the person that's taken statistics, like for instance, AIM took Math 341, maybe some other people did. You could use this experiment over and over again to estimate pi. I mean, you could, because if this is the probability is this, you do that over and over again to estimate the probability. Okay, well then you're going to know what you can solve for pi. It's just a funny thing. But let's open this up a little bit. So let's make this sort of big here, and this is the halfway point. So somewhere along here. Let me make sure I got the right picture. So I'm going to call the distance from the wall when we get it. I'm going to call that D. Okay, and it's going to be hard to. And then what? What's the other parameter here? So D and then this.
Once more. So what the point that you put there was just an arbitrary point between them. Like we're saying that's where
the center of the needle landed.
Okay, that's where the center of the needle is.
Yeah. So I can assume by symmetry that this is the halfway point is this is at or above the halfway point.
Sure. Yeah.
Because of what? Because of the condition that let me write that condition down. That the length of the I didn't write it down. The length of the needle this condition on it. The length of the needle is. I thought I said this D is the whole. It should be D over 2.
Is that the length of the needle or the like?
Let me check it because I'm sorry.
Or is that the radius effectively of the needle is D over 2?
No, the needle has a length. This D is where the center landed.
Right. No, I'm good there. But earlier you first wrote down that, then changed it to D. Yeah, so I'm wondering if the length of the needle is D, and then since we
L is less than equal to sorry, L is less than equal to D.
Right. Yeah. I imagine the D over 2 shows up because we're looking at it like a radius.
Yeah. So if the length, I recall this from years ago. If this is not true, the problem it gets more technical. So the length is less than or equal to D. So that's something important. Yeah. Thank you for. But this is we take this to be the center, and then the other variable theta. So so theta is uniform. So this is the D is that, but the theta is uniform from what to what? Well. You see, if you go, gosh, should have prepared this a little bit better. But certainly theta can't be less than 0. Now, if it goes the other way, if you picture it the other way, then that's also symmetrical. So it should go between 0 and pi over 2 for the theta. Okay, so why am I not considering this? Well, if it goes over here, now we're into if the theta as pictured is obtuse, then you see you would be doing the problem just on the other side. So there's a symmetry there. We can assume the theta is between 0 and pi over 2. So what is the qualification that with d and theta that you're going to hit the line? Okay, this is elementary trig. So are we missing? Is Ethan here today? That's quite usually he's. Oh, we're missing him. Okay, so what is the relationship here?
Okay, and one more thing, and in our example that we're looking at, that h is just
hypotenuse.
Right. Okay, sure. But the line itself is where we're like imagining the needle is going.
Yes.
Just for the sake of the
needle could be, it could.
Right. The needle is as long as it is, but yes. H is just in the direction that it's going.
That's just a hypotenuse to the sure. nearest.
Okay. So yeah, line. So we can imagine the angle being anywhere from being like parallel with the grid lines up to being perpendicular to the grid lines. And literally anything along there.
No. Parallel to the grid, because we can assume to pi over 2 is the max.
Right. Yeah. And if you just imagine going anywhere on that angle, you're going to end up getting the needle going in any direction there.
Yes. Yes. But okay. So what is the relationship? So cosine of theta? I don't know if there's a washout here or not. But cosine of no. So cosine of theta is what? It's d over h, right? So, and we have a hit. Okay, so h is did I do that right? D over h. So h is, I have to write this down, is d over cosine theta. And you have a hit if what? If h is greater than or less, then if h is less than or equal to the half the length of the needle, which is L over 2, then you're going to have a hit, right? Because this is, that's the center of the needle, and if this is the d over 2, so if h is less than that, then that means the needle will hit the line. Okay, is that okay? It's kind of quiet there, but
okay. I guess where I'm getting lost is we're disregarding something, and I'm guessing it's because of symmetry.
Yes.
And that's so going from parallel to perpendicular. Well,
like
the obtuse angle, yes. The other way. It's just symmetrical to something else, but it's different. But
yeah, it's going to be the same distribution. I mean, if the angle here, okay, so we can set this up where the angle is between 0 and pi over 2. Because if you want this, we do it over here. So if that, as written, if you have a obtuse angle, then we would have a acute angle going the other way.
I see that. It just feels like we're going to underestimate if we're not considering it. Like I just don't.
Well, no, I mean this.
I'm failing to see why we're allowed to disregard it.
Well, not really, because we're equating those cases with cases over here.
Okay.
Right? So, if it's like this, we're equating that with the angle you would get there you'd be hit, If you want to know the proportion of cases of theta and
okay. Thank you. No, that answers my question. So we're just looking at proportions. Okay.
Yeah, but we can definitely draw we need to draw a picture. But let's check what we have so far. So the condition on, I like to have this as a cosine function because I can draw that. So if I solve for, how about going? Let's do this. Let's put a d here, and I'll write cosine L over 2. Cosine theta. Okay, so if I can draw the cosine graph, so let's see, there's space problems here. I know where the theta goes. So what should we put? I would like to have theta be the variable on this side, and L over 2 cosine theta over here. And so this is your D. D. So D. So L over where's what is the cosine? So when cosine is 0, we're at L over 2, and when cosine is pi over 2, we're at 0. So this is the cosine curve here. So the question is, this is D. So the most D would be from this. The most D would be L over. Okay, so L over 2 is related to. What did I say? What did I say? The length of the needle was less than or equal to D, right? So the biggest L could be would be D. So D, the largest D would be D over 2. So D over 2 is up here. Okay. So this is the totality of possibilities. And we have to know which ones are the hit zones. So if D is less than L over 2 cosine theta, that refers to what? So I think the hit zone is here. So again, we're doing this by proportion. So we would have to figure out the area of the red zone over what? Over the total. So this is actually similar to what we've done before when we had a uniform distribution, just a box, right? But now when we have multiple, joint distributions, you don't get just a one-dimensional thing like this. You're going to get a rectangular structure here. It's a uniform distribution, but it's like it's supposed to add up to 1, but we want to know what proportion this is of that whole thing. So you actually have it's a two-dimensional, two-dimensional. It's a region. So it's a generalization of this. We have two variables here. Let's see. So what do we get as the answer here? I have to integrate something. So what do I have to integrate?
That's the cosine, or that the function is L over 2 cosine theta.
That should be easy to do, right?
Right. L over 2 cosine theta from 0 to pi over 2.
I have to multiply by the density function, right? So that area, but what's the total area here? So it looks like it's D over 2, so D pi over 4. So D pi over 4 is the total.
Why are we multiplying by that? I thought the idea was to divide by the total area.
Scale it, right. I meant to multiply by
its reciprocal.
Which I didn't do. So 4 over pi L. Okay, but then you're right, and I have to integrate this thing, which is L over 2 cosine theta d theta. And I don't know, that's a sine function, right? So L over 2.
Okay, hold on. Because we're multiplying by the reciprocal of the total area.
The total. So I want
the total area is like the box.
The box. So I got that fraction. What is that total area? It's D over 2.
I thought it was D times pi over 4, so we should have D times 4 over D times pi.
Hold on.
Okay.
The biggest D could be.
Oh, okay. Are we substituting?
No. Okay, so I need the entire. Let's just get this hit zone here, because it'll be that over the total area. This is complicated. The total is pi over 2 times D over 2. Yeah, it should have been. What we need to do is take. So you're right. I mean, I got to get that area over the entire area. What is that? Pi over 2 times D over 2. Okay, but then what is that top thing here? So this is sine, okay, so that's L over 2 sine theta from 0 to pi over 2, pi times d over 4. Okay, we good with this? So what's the final answer? So that's just 1. So it's 2L over pi d. Okay, so this, the red zone, the red stuff is this. So all of these are equally likely, okay? This is a joint distribution where the way you interpret this, this is a uniform distribution. So what's the chance you land in this region? Well, it's the area of this region over the entire area. So this is where you get a hit. In other words, when the needle intercepts the nearest line, and this is where you don't. So is that clear? So this hit zone here is this, which is L over 2. And then the entire area is a rectangle. It's d over 2 times pi over 2. Right? So the L on the needle could be less than d, right? L could be less than d, so we don't know. It could be as big as d, then we have a different picture. Does that make sense, or is it just cloudy?
I got it.
Let's see what could have caused people trouble here.
The biggest thing for me was just understanding what we were doing and realizing that we're setting up a proportion. So we're just kind of, without loss of generality, saying the needle lands above the halfway point. And then without loss of generality, it goes to the angle is to the right.
Yes.
Because it's going to be symmetrical regardless of that. And then from there, we're taking a proportion of where it could land.
The cases where it hit the line and the cases
exactly. Yeah. So understanding how we're setting up the proportion was a little fuzzy. I got it. I'm good to go. Once I had that, I'm like, oh, okay. Then we're just finding the area of that spot to the whole thing. I'm solid.
This example is actually, for those that might be interested in secondary teaching, you can actually have kids simulate this by dropping a stick, and they actually can approximate the probability, by repeating this many times. And then, like I said, you could then get an approximation for pi. And I wonder how many times you have to drop it before your approximation gets close. But it's something that they do in schools. I know I've been told, by teachers that this is, at least in the old days when they did enrichment type stuff. I wonder if anybody in our class did that in middle school or high school or something. Did anybody else encounter this problem? Anybody encounter it? Of course, they're not going to understand the calculus, but you can simulate this pretty easily. And certainly in tossing the stick, you will realize that the angle at which they say that the compass direction, whatever it's wherever it's going is independent of where it lands. You could check that too. Those are independent. Assume there's no gradient right to the floor, because how would that make a difference? Well, sometimes, if there's friction or something, it might line up along the gradient, but I don't know. Okay, well, thanks for enduring that. But this is sort of the reason for the jointly distributed, distributions of more than one random variable. This is so you can do neat stuff like this. Okay, let me check the chat. There could be like 5 million questions, which I conveniently ignored here. Luckily for us, the integration was pretty simple. But other problems, they could be more. What's the classic problem? What's the classic problem of this nature? I won't solve it, but just what's the classic problem? Maybe it's simpler. I don't know. But you have a similar thing, but you have a lattice of. Oh, gosh, this is not my day. You have a lattice of these targets, Okay, so it goes on forever, and you're going to drop a bomb on here with random coordinates, so X and Y are independent. You drop a bomb and say its kill radius is this. So I mean, this sounds like an awful thing, right? It's military stuff thinking, but the idea is, what is the probability that that bomb takes out one of these targets? So this is sort of a similar problem. You're going to use the symmetry, and I don't know. I don't think this is trivial, but it's probably not really hard. But this is the common problem. I mean, if you just estimate, just looking at it, what is the probability? Just looking at the way I drew it, it looks like it's pretty high, like 80% probability, something like that. That's a similar problem, right, to the needle thing. Instead of angle and position, now we just have X and Y coordinates are random. All right, okay. I found some interesting problem I was looking over the exercises more and trying to think, was there anything I could get out of this? And I found one that just caught my attention. I'll give it to you. Okay, so I'll have to copy out of the book here. You can see I really did a lot of preparation last night. So 5.32, it says that the time required to repair a machine, so repair time is exponential with lambda equal to 1/2. And they have an interesting problem here. So the B part says, what is the conditional probability? Calculate conditional probability that a repair takes at least 10 hours given what? Given that its duration exceeds 9. Okay, so don't just blurt it out. Or let's just say that's what you have to calculate. So we're dealing with these. Obviously, it's something to do with the memory list. So how can we write that? So X. So repair time X. X is the variable. So how do we write this? So X, what the probability that X takes more than at least 10 hours. This is continuous, so I don't have to put less than or equal to. At least 10, given that what? The X is already exceeded 9. Okay, let's just stop and think about this for a second. What was this memoryless property anyhow? So you don't have a hysteresis effect. So you're saying it's taken at least 9. What's the chance it's going to take more than 10? Let's think about this. So this was some memoryless random variable. So the fact that it's gone at least 9 means that the repair hasn't finished yet. So we're still in the game. But the remaining time, okay, so to go bigger than 10, so what would that be? Or bigger than or equal to 10 if it doesn't make any difference in the calculation, but let's just, so how about, okay, at least 9, so I'll do it this way. Okay, so I haven't heard from other people today. We have pretty good.
I don't want to just blurt it out.
Yeah, I know you know. Let's do it this way. So you guys are thinking about it, right? So, but it might help to write down the definition of memory list. So how did that work? So the probability that X is greater than S plus T given x is greater than t is the probability what? Probably that x is greater than s. So you assume that this is time and started somewhere and you've gone up to t. You've gone up to t. What's the chance that we'll do an additional s here? What's the chance that probably that it will take more than s? So it's going to be survive this period of s. So what's the chance? Okay, well, what was this? Remember, so this was the definition. So could we apply this stuff here? So what would t be in this case? 9 and s. So well, that's this. X is greater than, so what does s have to be? 1. So if it's memoryless, it has to have this. This is s. It has to have this property. So so what's s and t here? So in this case, well, I've done it. S and t are 1 and 9. Given that it's 9, so this is the same as a probability that it's greater than 1. So that's it. So we know that the exponential is memoryless. So we can just say what's the probability that it goes more than 1. In other words, intuitively, it's memoryless. You know that it's gotten to 9. What's the chance that it goes more than 10? Well, that's just, you got to get through that 1. That's it. And it doesn't matter what happened before. So the answer to this is just the probability that x is greater than 1. So I'll stop there. Is this okay? I hope I did it right. I'm just substituting into this definition here. So what would be that? How would we calculate that probability? Well, I don't know where the space is that I have. The space to do this. But what is the probability that x is greater than 1? And what is x? What is its density? What is its density? So x is f of x. What is the density of here? Of x is what? Is lambda e to the minus lambda x for x greater than or equal to 0 and 0 otherwise. Okay, so in this case, well, what was the formula we had last time? I don't have to keep, doing this, but
like the CDF?
Yeah, well, yeah. I think this is going to be okay. This is 1 minus the CDF at up to 1, right? So, but then what was the CDF? The CDF was 1 something. So I think this is just going to be E.
I wrote it down.
Yeah, it's just going to be
Okay.
lambda. What was lambda in this case? Lambda was a half. I think you just put. No, sorry, it's E. It's E. I'm just trying to remember this. When you subtract this off, it's e to the minus lambda. In this case, it's 1. That's simple. You see, when you take the 1 minus it, you get rid of the. In the CDF, you have a 1 in it. 1 minus something. So these 1s cancel out. I better have this right. So this is e to the lambda is a half to minus 1/2. Let me just check. I didn't do that. Sorry. I didn't do it. I just saw it in the book, so I don't know the answer. Let me check. Let me check the book. 532b. E to the minus 1/2. Yeah, this is correct. Now, maybe I should, if I'm a good teacher, I should do these steps here, okay? Because, it's
Kind of hard to do that with the limited board space you have.
well.
But-
Also, the critical thing washed out, so I feel I have to do it. So are people okay to this point? I'll fill in this. I'll do this calculation. Okay, I'll do the calculation, but I want to know if you're okay with the setup here. The intuition is it's already lasted 9 minutes or whatever they repaired, whatever 9 hours or something like this. And if you want to know what's the probability it's going to be more than 10, well, it's like starting anew at 9, okay? Because it doesn't remember that it's already consumed 9 hours. This model here is, and it sort of repair kind of goes that way, right? The repairman digs into your machine like it's a dishwasher, and then they find other things wrong, right? So, and whatever. This is actually this model. In my experience with appliance repair, this model is pretty good. Okay, it's not. The longer they go, it's sort of like you don't get an advantage there. It's like, oh, we worked on it for 9 hours, then it's going to be, for sure we'll be done soon. No, it doesn't go like that. But anyhow, I need to make this calculation over here, but I'm gonna have to erase something. I know this problem jumped out at me because we were talking about the memoryless stuff. So let me do the calculation. So what do we need to calculate here? Let's calculate this CDF. So f of x of u, what would that be? So 0 to u, lambda e to the minus lambda x dx. Okay, and this is what? Okay, so I integrate this density function over this region. Again, this random variable is 0 x less than 0. So this is minus e to the minus lambda x. This is the antiderivative of this. So I take the derivative of this, I get this. And I want to do that and evaluate between 0 and u. So at u, I get minus e to the minus lambda u, and then minus the evaluation. So minus this is a minus here, the evaluation at 0, which is 1. Okay, so that's 1 minus e to the minus lambda u. So you see, the problem we did here, we had 1 minus that because we wanted not the CDF but everything else. So everything, what's some of the probabilities of the outcomes greater than u. So for that we needed 1 minus f of the CDF. So it's 1 minus this quantity over here. What is that? E to the minus lambda u. And I think I was using that, e to the minus lambda u. So u was 1. And lambda in our problem, they gave that was...
it was 1/2.
1 over 2. Okay, so that was that problem. That one just sort of jumped out at me. But so what I need to do, and I hate doing it because it's work, and I don't feel like I don't feel so motivated. But we're always supposed to calculate the mean and the variance of any random variable that we present. So I guess we have to do it here, and it's a little bit complicated. I mean, this because of integration by parts, but I think I have to do this. Any questions so far on this? But getting back to that talk, I'm sorry. Sorry. The conclusion was, and it was sort of, it's not completely, rigorous, but their conclusion. This is just a weird thing. I don't know if you ever thought about it, but they say that more recently developed languages, more recently alphabets. When the alphabet comes in, they try to avoid homonyms, and when you go to the old ones like English, we got tons of homonyms. But then when you look at the Korean, I forget when I forget when the Korean alphabet was created, but it was like 1946 or so. I don't know. It's something recent. I mean, maybe that's wrong, but I don't, you know, but it's recent. It's recent, and there's much fewer homonyms. I'm sorry, I'm coming this off the wall, but that was the point of that talk. They were analyzing this, and they were saying something like, one of the reasons you get an alphabet or you do it the way you do it is to avoid the homonym problem, because homonyms can lead to some sort of, it's unclear what somebody means, right? If the word has the same sound, has different interpretations. Does that make any sense? I don't know. Maybe somebody said Korean language created by 1443. I'm not saying the language. I'm talking about the alphabet. That the representation by the, because this talk involved anagrams and okay, go ahead, speak. It's the alphabet. They're in the alphabet. Yeah.
The alphabet, but I can check.
Yeah, because the Japanese alphabet.
It was the writing system. Like I that's just from the Wikipedia page. He invented the writing. Well, not invented, but like he created the writing system in 1443.
Which is still pretty
new.
Yeah, I mean,
Okay, yeah.
you can look back at the Latin alphabet. That goes really far back.
Well, Hebrew, for instance, they don't have vowels, right? Because they didn't discover the vowel before. It's kind of hard to speak completely in consonants, right? But it's part of the that's a new. Anyhow, this talk was. It was all. It's like me, all over the place, with no focus. But it touched on some interesting things. So, the speaker was from Pomona College, so if you're there, you can afford to give avant-garde talks, right? You're not going to lose your position. Those are big shots over there. Hangul was not used by.
That's probably where your 1945 number is coming from. I'm also finding another article here. It was invented in 1443, or was it whatever that was? But yeah, it wasn't used professionally until much later. I don't know a ton. I took Japanese as my foreign language, but I know
that's older.
Okay. I know 14, that
14 something, right, or something. That's older, or 1300 something.
But I know that just the kanji, hanja, the Chinese characters are used in Japanese, Korean, and Japanese. But whenever it comes to how Korean is used, where you see it now, it's only the alphabet. They don't use Chinese characters really at all anymore.
Right. Well, one of the things that the speaker said was Chinese characters are not an alphabet.
Right. Yeah. It's a picture language.
Yeah. So that's so they didn't. That was not something that they considered, and they said there hadn't been any research much in homonyms in Chinese. Because you would expect not, right? Because it's a tonal language, right? So
right. Actually, and that's actually part of the reason why in Japanese they still use Chinese characters is to avoid homonyms. So there was actually a really big push in the 80s to do what Korea did and only use the alphabet, but people didn't like the fact that there were so many words that you couldn't tell which was which. And
you want it to be phonetic, right? You want it to be, it's easier. Phonetic,
exactly.
one to one.
But it didn't catch on because people really liked, I could tell what you're saying because of the Chinese character you're putting in,
yes.
As opposed to just writing it alphabetically.
Right. Well, I learned something. I don't know any foreign languages. So, but the authors of the paper, again, one was Turkish, one was German. There was one from Sweden, and Korean. So they actually had people who were native speakers to handle the different. It wasn't like, oh, I know when I don't know anything. Nobody just butt in and said, I'm going to say something deep about Korean when I don't know anything about Korean. It wasn't like that. That's something I would do. Be an idiot or something. But no, they actually had the paper had people. The experts. Their native tongue, so that was good. Let me see if I can find what were we supposed to do here? And it's difficult, right? So if x is exponential with parameter lambda, I could be supposed to get the mean, and we also need, of course, x squared. Now, the Ross, he loves to do two things at one time, two birds with one stone. I'm not feeling like that this morning, so I just want to get one thing out of this. So how would we do that? What's the definition? What is it? X e to the minus lambda x dx. So how do we integrate
Like
this?
integration by parts.
Yeah, but I've forgotten how to do integration by parts because I never ever teach calculus. So what should I call it? This is u in, should I call this dv? So what is this? So it's uv x minus 1 e to the minus lambda x uv from 0 to infinity minus the integral. I'll probably make a mistake at some point.
You're already going way faster than I'm going. I'm still finding v and blah, blah, blah.
Dx. V, so v du, but du, sorry, integral of v du, that gets rid of this. So uv minus the integral of v du, but du is just dx. So what is this thing here? So at infinity, this overtakes the x at 0, minus the value at 0. So that's just a big 0. But this guy is 0 to infinity e to the minus lambda x dx. And what is, so this is what? So you evaluate this. So, so minus e minus e to the minus lambda. So I take the derivative of this, I end up with this from 0 to infinity. And so at infinity, that's nothing, but it's 0, so this would be positive 1 over lambda. I hope that's right. I'll have to check the book to make sure. I'm pretty sure that's right. Okay, I'll stop here. Did anybody? Okay, so was there anything? Were we able to get this answer?
I'm working on it.
Okay.
Give me
Right.
1 second.
Yeah,
I'm trying
okay.
to like actually do it myself instead of just copying down what I'm saying.
Right.
I'm getting 0 minus. Okay, and then when we substitute in 0 here, we get e to the 0.
It's
So this
1.
becomes, yeah, it's 1, so we have 1 over lambda. The negatives cancel out, so we get 1 over lambda. Okay, I got the same thing. Yes.
Good, great. So we still don't have the variance. So
We have to just do integration by parts twice.
I hope not. I hope not.
Is there a way to do it without it?
Well, you want to, ideally you do this kind of thing recursively, and you realize something we've already done that we can use the way these things work, like for instance, we know that the integral of the density is 1. I mean, that could help, right? Because it's a probability distribution. So we got to keep in mind, so I don't want to, it's the problem of erasing stuff. Let's, okay, I just, you know what, this, let me just.
There is a way to, when I was doing linear algebra and differential equations, we had to do lots of integration by parts. And so we learned, at least for the exponential and something times a sine or a cosine, there's a thing called the tabulature method, which just makes it go. It's just a way that you look at the pattern of how it goes, and so you just do it. But
it actually is a critical thing if you're going to go on
Right. It's
in
good to know
statistics,
how to
because
do
you're talking
it.
about these are the moments.
Yeah.
You're calculating the moments, and that actually is critical. But I guess it's probably recursive or something like that's how you get it.
Yeah, it's just noticing what the pattern is, and so you just do it quickly. But
I don't want to do
yeah, I don't want to do it either.
I don't
I'm like, I don't know if I remember it very well.
But I want to know, what I would like to know is if I can just use what I just got, to help me here. So if I use parts with this new guy, so we'd have what? uv, so x squared minus e to the minus lambda x from 0 to infinity. Okay, so this is u in v. uv, so yes, and then minus the integral. I don't know if this will work, but I'm not doing what Ross did. He did what you did, Aim. So, but let me just see if I can cheat my way through this. So integral of v, so minus e to the minus lambda x du, which is 2x dx. So I think, let's check this over here. If you evaluate infinity, clearly the exponential dominates. And so this I think this still remains 0. So, okay, so what I have to, so this, supposedly if I've got this right, I have to integrate this. So let's pull out the 2 here, and then e to the minus lambda x x dx. Now, can I find what I had done earlier? Because what I did earlier had a lambda in it. So when I said earlier, when I got the mean, right?
Right. Yeah.
So if I can just put a lambda here and a lambda over here, so that cancel out, then you see I could cheat my way out because I'm this guy here. So this would be 2 over lambda times something we already did. That looks like the mean.
Right, which was 1 over lambda.
Which was 1 over lambda, right? So that's 2 over lambda squared. So let's see if we have anything now. So the variance, what's the variance then? So the variance would be that 2 over lambda squared minus the mean squared. And the mean was 1 over lambda. So that's 1 over lambda squared. Okay, so hopefully that's correct. So what do we calculate? So let's summarize what we did. So that's the variance, and the E is 1 over lambda. So these are the 2 creatures that we're supposed to get.
Well, I mean, I Googled it, so yes.
Yeah, so it's a slicker way to do this, I guess. But, these are moments. And it reminds me of Rachmaninoff, right? Musical moments, musical. Doesn't he have some famous piece? Rachmaninoff, yeah. Okay, so let's do another exercise, and then we'll call it quits for today. Okay, there was an interesting problem. Okay, I did find another interesting problem. We'll do this, and we'll stop at this problem. It reminds me of the one that you said Kelly Evans did, where you randomly, I forget what it was, you randomly cut a length of string, and you want to know what was the probability you would calculate?
Well, that came from 341.
Yes. Okay. What was that problem? How did it go? You have a length of string.
Yeah, let you just try to remember it. So, if you take a piece of string, oh no, it wasn't a probability question. The question was, if you cut a string randomly,
Yes.
what is the expected length of the string? As in the longer length.
Of the longest. So
yeah.
E.
What is the expected length of the long side?
There's something quite similar in the book, I think. It's funny how you change it just slightly, it changes the problem, but I think there's something that's similar. And then we'll finish on this. So what I'm looking at is 511. But this is a probability question, so it's going to be a little harder perhaps. So I'm looking at exercise 511. And what's the situation here? So you have a line segment of length L. And a point is chosen at random. Find the probability that the ratio of the shorter to the longer. So you're gonna take a point at random, and what's the probability that the ratio of the shorter to the longer is less than? Sorry, I got my eyes are not good. I think it's 1/4. Someday I'll do this problem, okay? Someday I'll get around to doing it, but right now I've got to stick with the book. Something funny happened. I was tired last night from, as you know, this committee where it follows me. I think I'm home free, and then the phone rings. But anyhow, I had missed when I copied the problem. I looked at the book and I copied really quickly. I wrote it down, and I had the problem the longer to the shorter is less than 1/4, and it can't be. It's bigger than 1. Bigger than or equal to 1. It was very funny. It's like, gosh, what? This problem doesn't make any sense. So I didn't read it closely. The one shorter over the longer is less than 1/4. So how does it? This is not hard, but let's finish with something that a feel good problem, right? Let me check the time. We can do this problem. So what is where would this happen? For which, so U is uniform. So U is uniform from 0 to L. So what would we require for? So we need the shorter. Let's rewrite this. I don't like ratios. Oh, hold on a second. Hello. Hello. Yes. The Medicare Health Fund, they will not leave me alone. Well, I don't even know what that is. You probably just want that. So, okay, so the shorter is, how to interpret this? So 4 times the shorter is less than the longer, right? It's the same thing. 4 times the length of the shorter one. So where does that happen? So we have to solve an equation here, right? So what region does that happen? So this is, say this is X. Oh, I guess we could call it U. We already have it. We already have it as U. So we need to have the situation that 4 times U has to be less than L minus U, right? So this is the shorter, and obviously this is the longer. So, it's a simple equation. So 5U is less than L, so U is less than L over 5. But there's 2 regions where that's going to happen. So what is the answer to this question? The answer to this probability. Let me check the chat here. Chat's clear.
New in chat, yeah.
Okay, so this is going to be equal to what? 2 times what fraction? What fraction is it here? Well, it's a fifth, right? So it's 2 times. So of the okay. So what is that fraction over L? So over L, what's the fraction? Well, it's 2 times L over 5. Otherwise known as well. The L's cancel out. The answer should be 2 over 5. I should check that to make sure I'm not lying. Maybe I should be honest. I should check it. Okay, actually, there was one other problem. Okay, just let me check my time. There was one other problem that I don't want to do it. I just want to give you a shortcut thing for it. Looking at 5.20. Okay, the story here is you have 65%. This will be my success probability. A population is going to, 65% will vote one way, and the rest will vote the other. So we're asking ourselves, what's the chance that a random sample so a random sample of 100, SRS of 100, in a random sample of 100, what's the probability that, so X is going to be binomial 100.65. So what is the probability that if you have 100 things that X will be greater than or equal to 50? Okay, what I want to say about this is that you don't need to, there's a couple things you don't need to concern yourself. When the numbers are big like this, forget about that continuity correction, just do it from here. And I would go like this. I would say 50 is less than equal to X, and I would just say less than infinity here. Because when you do the normal the normal, you standardize, you don't worry about this fractional things. It's going to be such a minor effect on the whole thing. So what kind of first of all, if 65% are in favor and you take 100 people, that's a damn good SRS sample. You can be very highly likely that you're going to get at least 50 people. But wait a second. Yeah, I mean, it's 50 is half, and you've got 65% in the population. So this is going to be a high number. What I'm trying to get at is you do this, you don't have to religiously follow the continuity correction, and you don't have to.
We wouldn't even need a continuity correction because it's already greater than or equal to. We use a continuity correction whenever it's X equals 50.
Well, not really, right?
Really?
Because you're going to approximate with a normal curve, right?
Right. Yeah, I'm with you there.
You want to get areas, so they usually go to here.
Right, and you get an area that's 1.
Yeah, they do that regardless of the.
Okay, but what I'm confused at is we already have X is greater than 50. We're already looking at an area that goes to the.
Right, but when you approximate, that's a binomial. But when you do with a normal curve, you want to shade it you want to go to 49.5.
Oh, I see. Okay.
You're trying to approximate with a smooth thing,
Got it. Okay.
But what am I trying to say? So, well, what do you do? So let's just, I don't know how much time I got. What do? You write this as probably, okay, so 50 equal to X less than infinity. But what do I need to do here? That's going to stay infinity. And this will be a Z. But this guy, you go what? You go 50 minus NP. So we know what that is, right? So N times P here is 65.
Right. Right. 50 minus 65.
Now, what goes in the bottom? And this is the thing to remember. Is the bottom.
p 1 minus p, so square root of that.
Right. The reason the square root is because it's just
It's just, yeah, we don't want the
that's the
variance,
way
we want the standard deviation.
normalization takes place. Okay, so you got to remember this. So we need the square root of what did I just say? 60 np times 0.35.
Whatever that is.
That's 1 minus p, 0.35. So notice for math people that NP, so n times p times 1 minus p, that would be maximized if p equals a half. And sometimes you make those, when you're trying to estimate things, say what's the worst case or something when when that standard deviation is the biggest, you say, well, just put it in as a half, because it doesn't make that much big of a difference in the end, as long as you're conservative, to do that. Okay, so what was this quantity? This I don't know, I need a calculator. We can. I guess I've never released you guys on time, right? You guys finish it, but I don't want you to get. I want you to realize that this approximation doesn't hinge on a religious, doing it.
But for what it's worth,
exactly,
you get like -3 for the z, so negative 3.14. Yeah,
negative
3.1. So it's very high. So we're asking for, okay, well, at least bigger than 3 standard deviations.
Right. It's a huge number. So what is it? 1 minus.
So 99 point, what is that for 3? It's 99.7. So 99.85%.
Well, it's 99.7%, right?
For between 3 standard deviations.
Right. So then what's left? It's 0.1.
What's left would be 0.15. Yeah. So 99.85%.
0.85. You see what you're saying is the answer?
99.85. Yeah.
99. Okay. This is 0.15%. Sorry, I'm tired.
Right. You're
right.
fine.
99.85%. Yeah, that sounds more like it.
So I have an exam to get to, so I do have to leave right on time. And
good luck on your test. Who you have? Who's?
It's for 490. Take care.
Okay, thank you.
Bye.
Okay, everybody else. I am thinking about how to build the test, and thank you for hanging in there. I've still got 10 diehards. Thank you so much. I'm sorry I was a little unfocused today, but I'll I'll make up for it on Tuesday, hopefully, and then get that test in your hand so you can start working on it. How many test questions? That's a good thing. I don't want a long test right now. I'm thinking of 5, but it's just, here's my problem. There's always this big cloud of chegg hanging over my head, and and this temptation that people have. I don't want to see anybody drink too much. It's temptation, right? Or gamble too much, or eat too much. Or use chegg too much. So that's why my tests tend to be on the long side. But I really am feeling like, for everybody concerned, including myself, grading these problems, maybe I should stick to 5. 5 questions are just carefully chosen so they're not automatic checks, especially not 20-minute check returns. That doesn't prove anything. It just proves that 20 minutes is a third of an hour. So that's my problem. I've already given you hints on some of the problems I would give you, right? The snippet of code, whether that's an ERP. So we'll get that one again. Hit that one again. And 5 is good, so we don't all have to just de-stress at McDonald's. I know if I go to McDonald's, it just causes stress because of all the salt and I'm old and I eat all the cholesterol, high blood pressure, all this stuff. It's definitely stressful to eat at McDonald's. I have to do it sometimes. It's the only thing open. And I get it. If you're young, just enjoy being young and not worrying about your health every moment. It's so good. Well, I think In-N-Out. I've heard